Okay, let's go ahead and do our first example of a comparing two means from two separate populations. So given in the table are the BMI statistics for, that's body mass index, I believe, for random samples of men and women. So this is a group of men and women. Assume the two samples are independent, selected from normally distributed populations, and do not assume the population standard deviations are equal. Okay, so we can do all of that. You can see that we have 43 people in both of our samples. That's nice, but it's not actually required. We see that we have two means and two standard deviations. So what we're going to be doing is asking ourselves the questions, are these two means different or are they about the same? So um, as we construct our null hypothesis and our alternate hypothesis, the null hypothesis is that the means of the two groups are going to be the same. And the alternate hypothesis, our default is not equal to, but otherwise we need to assume that it's something else. So I don't see anything in here about greater than or less than. So we just are comparing the two groups. So that means we go with our default that the alternate hypothesis is that it's a two-tailed test and they're not equal to each other. The test statistic for this is way simpler than the proportion one. All we have to do is notice it's a t-test statistic. It's just your first sample minus your second sample, just like before. But this time, it's just the square root of the first standard deviation squared divided by the first sample size plus the second standard deviation squared divided by the second sample size. So as you can see, and all the numbers they already have given us. So as you can see, it's way easier than the previous section. So let's calculate it here. I'm going to do parentheses for the numerator of the fraction. So it'll be 27.3677 minus 26.5702, like that. And then that's going to be divided by the square root of the first standard deviation squared, which is 7.875271 squared, divided by 43, then plus the second standard deviation squared, which is 4.840286, that squared, that's the standard deviation for the second population, divided by the sample size for the second population. So we do all of that, and we get a test statistic that is the correct answer of 0.57 if you round to 2 decimal places. So there is our test statistic. Okay, I'll skip the p-value, I'll skip the critical value this time. The critical value you can get from your t-table by looking up a two-tailed test. Actually, I am going to look up the critical value, because there's something important here. When we are doing this, we will have degrees of freedom, and the degrees of freedom is going to be 1 minus the smaller sample size. So before now, the degrees of freedom was always n minus 1. This time, it's going to be the smaller sample size minus 1. So in this case, it's okay because they're both 43. So that means we have 42 degrees of freedom. However, just be aware that if this had been a smaller number, like say 20, then we would have had 19 degrees of freedom. So you pick the smaller of the two, or if they're equal, it's just n minus 1. So let's go ahead and look up our critical value. We come down here to the t-table. The significance level is 0.01. So it's a 1% significance level. That's two-tail. So here's what we're looking at, 99% two-tail, 1% alpha. And 40 is the closest to our degrees of freedom. So 40. So our critical value is 2.704. Okay, so the critical value for 40 is 2.704. Okie dokie. So if our critical value is 2.704, you can see that we're going to fail to reject because our test statistic is not bigger than the critical value. So let's go ahead and look up the p-value. So to do that, we'll go back to content, websites for calculating it. And you see I have for section 9.2, I have something for doing the finding the p-value. Notice this important note I have. If you're doing a one-tail test, we need to divide the p-value by 2. So it's going to default to a two-tail test. So if you're only doing a one-tail test, you need to divide it by 2. So here we go. The sample mean for population 1 was 27.3677. The sample for the second population was 26.5702. The first standard deviation was 7.875271. The standard deviation for the second group was 4.840286. First sample size was 43 and the second sample size was 43. And we get a p-value of 0.573, and that is the correct answer. So 0.573 is the p-value. If we were doing a one-tail test, we would need to just divide that value by 2 in order to get the p-value for a one-tail test. So that's all you need to remember when you are using this calculator. And that's all you need to do is this orange box. You don't need to worry about anything else. So, as we expected, 0.573 is greater than our significance level. So that means we can't tell a difference between these two means. We can't tell a difference between the males and the females. There's not enough evidence, and you can notice that they started out being pretty close, and they had big standard deviations, so there was a lot of overlap. So what this means is that we're going to fail to reject the null hypothesis. And remember that when we fail to reject the null hypothesis, there's not sufficient evidence to reject the claim that the men and women have the same BMI. For all we know, they do have the same BMI. Okay, this next question asks us to construct a confidence interval, and so I am going to do that now. I don't have the formula for that at my fingertips, so I will look that up, and we will do the confidence interval in the next video.